All right, so my name is Eoin Carley. I am a research fellow at the Dublin Institute for Advanced Studies, and I use LOFAR to study eruptive activity on the sun. I use LOFAR to study CMEs, flares, and all of the radio activity associated in terms of plasma emission, in terms of gyrosynchrotron emission, and any other type in between. So this talk will be about solar radio emission mechanisms. And before I even go to an overview, it's important to remind ourselves of why that's important. So when we observe the sun, we can observe a variety of different types of activity, both quiet sun and active sun. When we observe from high frequencies to low frequencies, the sun can take on a variety of different appearances in the radio domain, especially in the quiet sun. You can see at the top there, from 17 gigahertz to 80 megahertz, it looks different. When we observe the active sun, we can have, very bright and very large radio sources like the ones on the bottom of the slide there. And it's important to ask ourselves the questions. I guess generally all of astrophysics should ask this question: is what is the origin of this light? And what happened to this light on its journey to the observer? And this is to do with the radio emission mechanisms themselves and how they propagate from the source to observer. Now, as in other domains in the radio domain, if you can answer these questions, that usually gets you back at really important diagnostics such as temperature, density, distribution functions of the particles, and particularly important for the corona is the magnetic field there. So the sun or the radio domain is one of the only means, or one of the very few at least, that provides access to measurement of the magnetic field. And that again depends on what radio emission mechanisms that we have. Okay, so this talk will basically be about three of the main types of emission mechanisms. So before I get into the emission mechanisms themselves, I have to go through, as you can see here, some fundamentals and preliminaries, and this will be a little bit of a whistle-stop tour through, some essential formula that we need to move on to emission mechanisms. So some of it may be pretty familiar. If not, and I'm going pretty quick, don't worry, I've left in references and some essential reading material. So I'll talk about fundamental frequencies in a plasma, the Rayleigh-Jeans law, which we may have heard of before, especially if you studied radio, brightness and effective temperature, and a very small bit about radiative transfer. And then I'll talk about three main mechanisms: thermal Bremsstrahl law, which is, the primary one for the quiet sun. It's not the only one, but it's the primary one. And then ones that are important for solar flares are the gyromagnetic emissions, of which there are three flavors, and I'll describe them. And then most important for the low frequency domain, particularly LOFAR observations. As you saw in Diana's talk, it's an awful lot of plasma emission. So I'll go through the details of how these things are generated and what kind of physics we can get out of them. And please do also interrupt if you have any questions throughout. Okay, so fundamentals and preliminaries. The first thing we need to talk about is, fundamental frequencies that we have in a plasma. If you studied plasma physics or MHD before, you probably will have come across these concepts, but we'll go through them anyway. So the first and probably the most important frequency or oscillation one can have in a plasma, and extremely important for the radio domain, you'll come across this time and again, is the plasma oscillation. So imagine we have a soup or a sea of electrons represented by this blue cloud here. And we have a bunch of protons represented by the red dots. And if we displace the electrons, or they get perturbed with respect to the protons, this sets up an electrostatic field. All of the electrons feel that electrostatic force, and they'll accelerate in the direction of the arrow that you can see there. They overshoot equilibrium, and they feel the force in the opposite direction. If you allow them to keep accelerating in this way, this sets up a simple harmonic motion. Hopefully you can see the little movie illustration at the bottom there as well as I can. And it's basically a collective simple harmonic motion of the electrons with respect to the protons over time. Now, the frequency at which this happens is pretty simple, but it's an important formula, and it basically depends on the electron density and some constants here, like the electric charge, electric mass. Now for the corona, take a typical density of an active region of 10 to the 9 per cubic centimeter. That frequency ends up being in the low frequency radio domain. So low frequencies, or radio in general, is pretty privileged to be able to probe directly one of the most fundamental frequencies in a plasma, in the corona. So this density here will give you 284 megahertz plasma frequency, for example. The second most important frequency, and one you come across all the time, so these two are, you can't read through a radio physics paper without seeing these things, is the gyro frequency. So in a magnetic field, if we place a charge in this field, it will feel the effect of what's called the Lorentz force. Now I'll go into what exactly that is, but this causes the particle to gyrate, like you can see in the movie here, opposite directions for opposite charges. For the electrons, the frequency of that gyration depends on the electric charge, the mass, and the magnetic field strength. We can simplify it to this formula here, where B is in Gauss and F is in Hertz. So say for an active region magnetic field, this is actually pretty strong in an active region, 1,000 Gauss magnetic field gets you at a gyro frequency of 2.8 gigahertz. So again, radio gyro frequency happens to fall inside the radio domain. So radio is an extremely useful domain of the spectrum that gets you at two of the most fundamental frequencies inside a plasma. Okay, so we've maybe all come across these before, but it's important to remind ourselves what exactly they are, because I'll be mentioning them throughout this lecture. Okay, second bit of my preliminaries, I'll talk about the Rayleigh-Jeans law, and this starts to get us a little bit closer to a thermal emission mechanism. So in quantum mechanics, we may have come across before Planck's law, which is basically the spectrum produced by a black body. A black body is one where you absorb as much radiation as you emit. It's in thermal equilibrium. And the photon spectrum it emits is a thermal photon spectrum. This is what Planck's law describes in specific intensity here. In specific intensity versus frequency, its spectrum takes on this characteristic shape, where we initially, down in the radio domain, have a frequency squared dependence, and then it drops off here. And you can see different temperature dependencies as we go up here. So for example, 10 to the 6th, this would be a thermal spectrum for the corona. Now in the low frequency limit, we can basically take the photon energy is much less than the thermal energy of the plasma basically, and simplify Planck's law into what we call the Rayleigh-Jeans law. And that's kind of the thermal spectrum that we always come across for in the radio domain. So basically in the radio domain, in the blue shaded region here, if you observe a thermal spectrum, it will have this nice frequency squared dependence here, which you can see here, okay? And this also gets us at, a really important aspect of studying radio astronomy, particularly for the sun or quiet images of the sun. The images and data that you sometimes see aren't often given in terms of intensity, specific intensity, or in flux. They're often given in terms of Kelvin or brightness temperature. So the brightness temperature that we see is basically how hot a black body would have to be to observe the intensity that we see. And it's just a simple conversion between the intensity of a black body spectrum in the low frequency limit and the temperature that we see here. This is known as the brightness temperature. It's a concept you come across all the time, particularly for imaging maps of the radio sun. Okay, so the last bit of preliminaries and fundamentals I want to go into here is a little bit about radiative transfer, and also the concept of effective temperature, which is a little bit different from brightness temperature. So what is radiative transfer? So radiative transfer it's a vast subject. It gets pretty complicated, and it doesn't only apply in the radio domain, of course. It's all domains of studying the change in the intensity or the specific intensity of your light from source to observer, okay? And the primary formula that we'll worry about here is the change in intensity with respect to path length along the line of sight. So suppose you have a source here emitting in a specific intensity. We're basically asking what's the intensity received at your telescope. It changes in a few ways. So imagine you have a cloud of gas or plasma in between the source and your telescope. That could be the interstellar medium. That could be the solar corona itself. Doesn't matter what it is. It's a plasma between you and the source, and it contributes in a couple of ways. So it can either contribute by emitting intensity itself, in other words, a positive contribution. That's what we call the emissivity, usually ascribed J-nu, depending on frequency. Or it can absorb or take away from the light that was originally emitted at the source in terms of the absorption, or kappa nu, this is usually called. So J nu, the emissivity, is a positive contribution to that intensity change. Kappa nu is a negative contribution to the intensity change, hence the negative sign here. Now, one of the most important functions that's often constructed in radiative transfer is something called the source function. It basically tells you the emissive and absorptive characteristic of a cloud of plasma, and it's basically given by the emissivity over the absorption. Now, that always doesn't have to be associated with a thermal spectrum or Planck's law or Rayleigh-Jean's law. That can actually be any character of spectrum or source function, it could be non-thermal. But nonetheless, what we do in radio is we associate it to a Rayleigh-Jean's law so that we can get at something called the effective temperature. So while we had the brightness temperature was associated with that Rayleigh-Jean's law intensity, the effective temperature is associated with the source function. And like I said, the source function can be non-thermal. So the effective temperature that you actually measure from the sun can be non-thermal as well. It can be 10 to the 9 Kelvin. It can go all the way up to 10 to the 15, 16 Kelvin. Clearly not a measure of the temperature, in the source. This is just a measure of, the non-thermal nature of the source. So those are the two concepts of brightness and effective temperature. And that you come across them pretty regularly in radio radiative transfer or radio physics in general, especially when talking about source intensities. The last thing I want to go through for radiative transfer here is the concept of optical depth, which is probably familiar to a lot of people. It's the integration of absorption along the line of sight. So if we integrate all the absorption we receive from source to observer, that's called the optical depth. It's a unitless value. It's kind of a measure of how opaque or transparent a source is. If a source is opaque, this is much greater than 1. If it's transparent, it's much less than 1. It tells us how much absorption is in there. Now, the reason why I talk about all these things, so from radiative transfer, effective and brightness temperature, and optical depth, is that we can actually rearrange these formulas and get at some pretty useful characteristics of the intensity we see on the sky in the radio domain. Let's take, for example, an isolated thermal source. We can use these equations, and I haven't showed it here. I've actually left it in some supplementary slides if you're interested. And an optically thick source will tell you that the brightness temperature is equal to the actual electron temperature in the plasma that we're seeing. This means that, the radio domain is a really excellent measure of temperature in the solar corona, and you see that with temperature maps of the solar corona. So I show here an example of one such map at 270 megahertz from the MWA, or Murchison Wide Field Array. And you can see here the color grading here is in the megakelvin range. It tells us basically the temperature of the corona, and it's a really nice and accurate measure of getting at that temperature, as opposed to using EUV spectroscopy, for example. In the optically thin domain, when this would be a tau, it is much less than 1. The brightness temperature is much less than the temperature of the gas, and it's much less by a factor of tau. So be careful if you're looking at optically thin material in the radio domain. The brightness temperature that you see at the telescope isn't always a direct measure of the temperature of that plasma in optically thin. Okay, so that was kind of a quick tour through, Rayleigh-Jean's law, brightness and effective temperatures. If it's all very familiar, that's great. If not, then these are some essential reading material down here I mean, in fact, this paper here discusses it really well, and it's kind of essential for any solar radio astronomy course. Okay, so this kind of gets me close to the appearance of the radio sun. Why does the sun look like it does, especially the quiet sun, in different frequency ranges? So I showed here why, when you look at the sun, its brightness temperature is a measure of temperature in the corona itself. Now, but when we kind of change frequency, you may have noticed before that the appearance of the sun changes, and I'll show a little movie here to see to show you what I mean. So, say for example, at 300 megahertz, the sun appears as a diffuse blob, as Diana showed in her last lecture. So this isn't just an effect of low frequency or low spatial resolution because of low frequency. I'll show why that is. And also during the movie, when we go up in frequency, you'll see that the sun, radio sun, becomes smaller, and the brightness temperature also drops, or actually the actual temperature of the atmosphere also drops. So let's take a look at this. So hopefully you can see that movie playing. And as we go up in frequency and reach 17 gigahertz, we actually reach the chromosphere. And say go down in frequency again, we end up with a much larger radio sun in the corona. And it goes from around 1 million Kelvin to around 50,000 Kelvin in the chromosphere. Okay, so what I want to describe here is the reason why the radio sun looks this way. Why is it that when we go from, a few hundred megahertz down to a few tens of gigahertz, we just see a different radio sun, and the brightness temperature changes. Now, in order to describe why that happens, there's a couple of things I need to do. I first need to go into the first emission mechanism that we're interested in, especially the quiet sun, and then we'll go on to a little bit about scattering. So the first emission mechanism we're interested in, particularly for the quiet sun, is Bremsstrahlung emission, or otherwise known as free emission. So for the quiet sun, this is the dominant radio emission mechanism. It gets its name because we have free electrons zipping around the plasma, and they're able to undergo deflections in the presence of other charges. That deflection is an acceleration, and an accelerating charge will, emit radiation or a photon. Now, it's pretty involved. In fact, Shane went through Bremsstrahlung in the X-ray domain yesterday, but I'll just quote what the emissivity and absorption is for a thermal distribution of electrons. Okay, so for a Maxwell-Boltzmann distribution in a plasma, when we have a lot of electrons, emitting free radiation, they have this emissivity here and this absorption coefficient here. And these are, quite long. I'm not going to go into them in any detail, but just to show the emissivity depends on the number density of free electrons and the number density of ions, and is inversely proportional to the temperature. I won't concentrate on this too much, but I will go into something that's a little bit more important for the quiet sun, and that's the absorption coefficient. There's a huge amount of parameters here. I'm not going to describe them all, but I'll show you on the next slide here when we evaluate those parameters, what we're left with. So this is a much more simplified and reduced version of what absorption is like in the quiet sun due to free emission. Okay, so we have its absorption is directly proportional to electron number density squared, inversely proportional to frequency squared, and temperature to the 3/2. We can take our formula for optical depth and integrate this along the line of sight. We will get K nu L for constant absorption along the line of sight, and we're left with this formula here. So this basically describes that, when we move to higher frequencies, we see deeper and deeper into the solar atmosphere. We start at the we start at the corona for low frequencies, and higher frequencies allow us to move into the chromosphere. And basically it's described by, increasing frequency here will make the optical depth drop, meaning that we can see further along the line of sight into the solar atmosphere. So I'll play that movie again here. We start at 300 megahertz. This would represent where optical depth becomes 1 for that frequency. But moving into higher frequencies, we can see further and further along the line of sight because, the opacity drops as we move in frequency. So that's the reason why, in going from 300 megahertz to 30 gigahertz, we go from corona to chromosphere. In fact, the density ramps up at the chromosphere so much that we can't see past the chromosphere in the radio domain. So the radio will only ever get you to the chromosphere and never beyond, mainly because of this fact here, because of the nature of free opacity in the solar atmosphere. I should say as well that this isn't the only source of emission and opacity in the quiet sun. We also have gyroresonance absorption, which I'll talk a little bit about, and that's probably the reason why this active region here is particularly bright, is gyroresonance emission and absorption here. So, well, for the most part, free emission is the emission you're seeing for the quiet sun, from corona to chromosphere. And there's a nice review of this in Shibasaki 2011. Okay, so that describes why we can see further into the atmosphere with increasing frequency. Well, I want to just spend a slide because it's an important one, describing why in the low frequency regime, the sun is just, it looks pretty boring. It's like a big cloud, nebulous blob, whatever you want to call it. It just doesn't have definition, okay? We can't see fine scale structure. Now, you may legitimately think that this is just because in low frequencies are in long wavelengths, we just don't have the spatial resolution in our interferometers. Hence, it ends up looking quite diffuse. But actually, the theory goes, even if you had very long baselines in your interferometer and you had very good spatial resolution, you would still see this, diffuse blob. You would never be able to see small scale structures in the quiet sun at low frequencies. And there's a good reason for this. And this is to do with scattering and also the refractive index of the radio in a plasma. Okay, so the refractive index in an unmagnetized plasma, that's pretty important, is given by this formula here. So the square root of 1 minus the plasma frequency squared over the frequency of the radiation squared. Okay, so what is refractive index? It basically tells you what the phase speed of your light is with respect to the speed of light in a vacuum. And like we have, in the lab, when you use visible light in glass, if the phase speed at this interface changes, by Snell's law and the refractive index, the light will bend and it will change direction and change path and then change again once it exits this glass. This is kind of exactly the same mechanism given a non-unity refractive index for radio in the solar corona. Radio waves encounter blobs of plasma in the corona, and they undergo this effect. They refract and bounce, okay? It's pretty detailed and pretty complicated, and you can see the detail in this nice paper by Edward Contar here. But the effect is that if we have a really small source in the corona, the light is emitted every which way, but it undergoes numerous refractions and scatterings until the final source that emerges is actually pretty large, okay? So we don't have the ability to resolve small sources in the corona. They just don't exist. Scattering makes them really big. And it's the reason why the radio sun is really diffuse, okay? Another important point here is that, if we have a radio frequency less than the plasma frequency, the refractive index becomes complex. By that I mean it's an imaginary number, meaning radio waves don't propagate. Okay, so it's also another source of radio waves having an inability to escape the corona. So it's pretty in depth, and there's a lot to it, and I've only just scratched the surface of it here, but you can read about it in this paper here. So these two formulas here that I just described kind of describe the appearance of the quiet radio sun almost in a nutshell. There's more to it, but the reason why as we go down in frequency, we see further into the corona and eventually the chromosphere is because of the changing optical depth with frequency and inverse frequency here, okay? So 17 gigahertz, you image the chromosphere and any filaments, and out at 80 megahertz, you image the corona and it's quite large. The refractive index also tells you that it's non-unity, meaning phase speed of radio waves change as they propagate through their corona, meaning they bounce and they scatter and they wash out any fine scale structure. And that pretty much describes the loss in fine scale structure or small features as we go into the low frequency regime. That's a little bit debated nowadays. You know, if we did have very long baseline interferometry, can we resolve small scale sources? There's a good few papers starting to be written about that nowadays. The answer, I guess, is maybe we can, but for the most part, it looks like, you know, a nebulous cloud. There is no fine scale structure on the quiet zone.
Oh, and can I ask you a question? What is
Yeah.
what's the dotted circle?
Oh,
Is that the measure of the refraction at those wavelengths?
in the MWA image here?
Yeah.
I'm not so sure. I'd have to go back to the original paper. My guess would be that this is the predicted tau equals 1 for 80 megahertz, where we expect 80 megahertz to be escaping the corona.
Okay. Because I see on the left one, it's very close to the optical side.
It is.
Yeah. I think if I remember the paper, it's a plasma shell. So yeah, indeed, it's what you would see. I mean, it's basically based on density models. What would be the height of the plasma emission at 80 megahertz?
Okay, and then you can see it kind of goes a little bit beyond that too. So those kind of a good point. The density models are kind of a too simple description of how the corona actually is. Great, thanks, Pietro. Okay, here. What time am I on here? Okay. So that was the quiet sun. Yes, let's have a recap here. So I gave a quick tour through some of the, you know, fundamentals we need to study the quiet sun and our first radio emission mechanism, and that's thermal Bremsstrahlung. So in a nutshell, if you think quiet sun in the radio, this is the emission mechanism you can go to. It's not always that way, especially in active regions. You can also have what's called thermal gyroresonance emission. And that kind of gets me into the next set of emissions. These next set of emissions are more important for energetic activity on the sun. So when we have energetic particles, non-thermal populations of particles, what are the emission mechanisms that we see, particularly with regards to flaring and with regards to CMEs or any other kind of eruptive activity? These emissions here, I'll go through them. There's 3 flavors of these, and usually associated with the microwave regime. Plasma emission is more associated with low frequency observations of the sun. So I'll go through these separately. Okay, before I do, it's important to remind ourselves of, you know, the physical mechanisms of what's going on in a flare or a CME, and where we get energetic electrons, and, you know, where they might be associated with radio emission. So this is a nice illustration from this paper here, and it shows a, you know, a typical flaring loop, and we have usually reconnection in the corona. This accelerates electrons. You might see a coronal X-ray source, hard X-ray source associated with those electrons. The electrons what would you call it, plummet into the atmosphere, and as they do so, they spiral. When they hit the atmosphere, hit the chromosphere, you get these thick target hard X-ray observations that Shane talked about yesterday. But those same electrons that produce the hard X-rays are almost the same. As they spiral down into the atmosphere, they emit what we call gyromagnetic emissions, and they may even emit plasma emissions. But for the most part, for the, you know, low atmospheric heights, we're going to talk about gyromagnetic. So this provides a diagnostic of, you know, flaring loops in terms of the energy of the particles, as I'll show, the magnetic field, which is super important, density, temperature, all sorts of things, and also it's a complement often to the X-ray observations that are observed almost simultaneously with this process. Okay, so that spiraling motion in, you know, a broad sense is called gyromagnetic emission, and I'll show the 3 different kinds based on energy. But first, a little bit about the Lorentz force. So I showed this movie at the start. we have a magnetic field here, and a particle traveling through that magnetic field will feel something called a Lorentz force, which is its charge and V cross product B. So basically, if you cross its instantaneous velocity in this direction with the B field, you get a force that's inwards here. This represents a centripetal force. Sorry, there's a question there. Yeah. Mohammed?
Yes, please. I have a question about the difference between the gyromagnetic emission mechanism and the plasma emission mechanism. So I was wondering if can we differentiate between both mechanisms by another way than the frequency range?
Usually the intensity is a good indicator. The gyromagnetic emissions I'll talk about here are what we call incoherent, meaning their brightness temperatures tend to be not very high, you know, whereas when we observe plasma emission, the intensities are really high. They're non-thermal and they can be up at 10 to the 9 Kelvin, even as high as 10 to the 15 or 16 Kelvin. So you're right that where they're looking at their intensity with respect to frequency, as I'll show, is usually a key indicator of these mechanisms, but there's also the intensity. There's different levels of polarization expected from them as well. So yeah, there's a few different ways of diagnosing these things, and I'll talk a little bit about them in the next few slides.
Yeah, maybe I can just add that very often you wouldn't be able to see the gyrosynchrotron emission in the dynamic spectra observations, because there's
sometimes but it tends to be weak, you know.
Yeah. Thank you.
Yes, so the Lorentz force is, where was I? Yes, a centripetal force, and it causes the particles to gyrate in a circle, okay? And if they have a component of velocity along the B field, you'll get this helical pattern. The acceleration they experience is proportional to the magnetic field, which is quite important. The power that they emit is given by the Lamore formula. So this is power per unit solid angle of electromagnetic emission from an accelerating charge. So this is actually a really handy formula relating power emitted to the acceleration. An important fact about this is that power then is inversely proportional to the mass, of course, of the particle. Because the electrons are so much lighter, they are millions of times better at producing electromagnetic emission. Hence, we see electromagnetic emission from the electrons. And actually, that's just a general fact, not just for gyromagnetic emission. So the electrons are much better radiators, and generally, this is where the emission comes from. So in order to understand, what we want is basically, as Mohammed pointed out, is intensity with respect to frequency. That's usually a key indicator of what we're actually looking at. So let's talk about what kind of intensity with respect to frequency we have for these emissions. So I'll start off, first of all, we have a single electron and a monoenergetic case. So this is super simplified and unrealistic, but we'll build up from there. And we saw in the Lamore formula, which is power per unit solid angle, we have this sine squared term here, meaning that a particle gyrating, a non-relativistic one, in a magnetic field, it experiences a centripetal acceleration this way, and it rotates this way, which I'll show. Its radiation pattern is actually a dipole, okay? Meaning that you see lots of power here. If the particle then rotates a little bit, you would see no power here, okay? Now, as it goes on, you would see more power again. And in fact, over time, the power that you receive from that electron is sinusoidal, okay? So it's just a simple sinusoid. So that's for monoenergetic, non-relativistic case. And there's a nice description of this in Dale Gary's radio astronomy course here. Now, we want power with respect to frequency, because at the end of the day, frequency and power is what we really measure with in radio astronomy. So how do we get that? It's just simply the Fourier transform of this. This is what we have over here. It's power with respect to frequency. So in this really simple case, the power spectrum you would see is just a spike at the cyclotron frequency that I gave before. That's what you would measure if you had a single electron monoenergetic, okay? But that's, of course, a little bit unrealistic, especially that we have high energy electrons in solar flares. So we need to go into a relativistic regime after that, okay? The Lamore formula becomes a little bit more complicated, but it's the same thing. We have power per unit solid angle and acceleration, except this time, instead of just our sine squared term, we have a few different terms, including some term, this Lorentz factor out of relativity, okay? So it's a bit involved, but what happens is the electron radiation pattern isn't anymore dipolar. It's kind of beamed into one direction. All the power is kind of just beamed into this narrow beam here, okay, with very little power on the other side. So, and the beaming, in fact, is the opening angle of the beam is given by 2 over the Lorentz factor. So if you were observing this single electron relativistic, you would see all the power on one side of its orbit, and then as it swung around again, you would see none. In fact, the power with respect to time would just look like this. You would see a lot of power here, and then none, no power, and then a lot of power again. Now, as we did the last time, if we just take the Fourier transform of this, this is the power with respect to frequency that we see. This gets us a little bit closer to gyrosynchrotron and synchrotron spectra, okay? And then we don't only have one harmonic of the cyclotron frequency. This time we have many, many harmonics, and it takes on this characteristic shape. The Fourier transform of this isn't a sinusoid because there's obviously a lot of different types of frequency powers in there. It actually looks like this. Okay, so let's be a bit more realistic. We have our relativistic single electron. Of course, in a plasma, we have an ensemble of electrons with a distribution function, not just that one energy, okay? So in reality, what we do is we take into account the fact that there's a distribution of electrons at a variety of different speeds here. It could be thermal plus a power law here given by the spectral index. And we take those gyro synchrotron or synchrotron spectrum, all the individual ones that you just saw before, and they each contribute to the overall synchrotron spectrum, meaning synchrotron spectrums have an emissivity, at least of intensity versus frequency, a bit like this. And I'll show what the actual one looks like. So this is just the emissivity here, and it tends to have a power law distribution in intensity. The usual way in which we interpret this, we usually look at the distribution of intensities and try and get back at the distribution of electrons, both thermally and non-thermally, as well as other parameters of the plasma like magnetic field, which I'll show. Now, the problem with gyromagnetic emission is that it's complex and it doesn't have a general theoretical treatment that kind of covers all energy ranges, and it's just a single neat formula. So in reality, it's split up into 3 different energy regimes here. So for example, gyroresonance or cyclotron emission, you'll often see that for quiet active regions with thermal emission. This is the emission, gyromagnetic emission produced when you have a thermal distribution of electrons, okay? And it's usually non-relativistic. The one that's most important for the sun is called gyrosynchrotron emission. That's for mildly relativistic and usually a mix of thermal and non-thermal particles. In other words, the electrons will have a thermal distribution plus a non-thermal tail. And usually this is what causes the gyrosynchrotron emission for the sun. Typical energies of a few hundred keV and probably up to more than this, maybe a few MeV as well. In high energy astrophysics, then we have synchrotron emission. That's usually for highly relativistic, non-thermal electrons with a very nice power law tail here. And for the most part, we usually don't encounter this on the sun. Sometimes we do, but it's because it's such high energy, we don't come across it that often. So it's the gyrosynchrotron emission that we have to worry about here. And it's the one I'll describe in a little bit of detail here. The point is there's no single treatment of all 3 of these things here. You have to go into them separately, theoretically. Okay, a bit of gyrosynchrotron theory and what it depends on. So it's a bit involved and complicated, but I'll just describe the simple elements of how it's done here. Usually we have, some source here with a B field running through it. We observe at an angle with respect to the B field theta. The source has a size of omega and usually a depth L. We have a plasma density MP. We usually have an energetic electron number density and star here, and then electron spectral index and max and min energies of those energetic electrons. The goal in gyrosynchrotron theory is usually to work out parameters we came across before, emissivity and absorption. And on face value, these are actually pretty simple. They depend on the number of energetic electrons. You know, will give you more emissivity. That will actually give you more absorption as well. And the magnetic field as well will be scaled proportionally to emissivity and inversely with absorption. Okay, so if you work out absorption and emissivity, in other words, if you measure the intensity coming from a gyrosynchrotron source, you can get back at these parameters, which is super useful. The complication comes in these terms here, and I show them here, you know, not to actually go through them in any detail or understand them, but just to show you what's involved. It's pretty complicated, but there are some familiar parameters here. We have the velocity distribution, and we have the pitch angle distribution, and these look pretty complicated, but they're kind of just expressions that take into account the observing angle and some relativity factors here. Okay, you know, we can't go into them all here, but the process is to numerically integrate this, so you know how intense your source is with respect to magnetic field and number of energetic electrons and so on, and that provides a diagnostic of all this stuff. It's quite involved, as you can see, but I guess the original paper that everyone should go back to if they're interested is Remedy in 1969, and there's some other more modern papers that are really good as well that kind of go into this in more detail. But we can forget about the really complicated theory. I mean, what does all of that give you? When you measure a gyrosynchrotron spectrum, it has a really characteristic shape, and this is one of the most information dense spectra that we really have for the sun, because it depends on a huge amount of parameters that we can diagnose. So here we have flux or intensity integrated over source size versus frequency. On a gyrosynchrotron spectrum, when we observe it in a flare, it looks like this. So we have a peak source of, it will have basically a power law on one side that we call the optically thick side of the spectrum. You'll see this terminology in papers all the time, and it has a peak, and then it descends again on the optically thin side of the spectrum. Okay, so the arrows here, this is just an illustration of a typical, you know, what one would look like. The arrows indicate the direction this whole thing would move if you say increase one of the parameters. So for example, if we increase the magnetic field in the source, it moves up and to the left. You get more flux and it moves over this way. Okay, if you increase the source size, the whole thing would move up this way. You know, you just get more radiation in general. Okay, so this kind of illustrates the point that each characteristic part of the spectrum here, the peak flux, the peak frequency, the slope you see on this side and the slope you see on this side, is dependent on the original parameters in the plasma. In fact, I've listed a few of them here. So for example, peak flux and frequency, that gets you at the magnetic field strength and column number density and a few other parameters. The slope above F peak here is a really important one. This can get you back to the non-thermal electron spectrum. Okay, the slope below the peak is a really complicated matter. It depends on many things, which I can go through very briefly. How am I doing for time? Yeah. So this low frequency turnover here that you see in a gyrosynchrotron spectrum, it depends on a huge amount of things. It's because it's the low frequency end, it's optically thick, meaning the radiation doesn't escape that easily. It's just affected by so many different parameters inside the plasma. So the low frequency turnover and slope depends on gyrosynchrotron self-absorption, which is the energetic electrons themselves reabsorbing their own radiation. Okay, Racine suppression is a popular one you will see in this theory. It's a bit complicated, but it means the phase speed of the radio waves exceeds the speeds of the electrons, and it quenches the emission, and it leads to an even steeper slope on this side. Okay, You can get gyroresonance absorption. That's the surrounding environment, just the thermal electrons reabsorbing in the gyroresonance mechanism. Free absorption that we've already come across, that can happen as well, and emission below the plasma frequency. Okay, so there's a lot there, but the point is the shape on this side, you often see people interpret it in many ways, maybe without taking into account that all this can happen. So the point is, if you're studying gyrosynchrotron spectra, be really careful with that side of the slope, okay? For an excellent discussion of this, Klein 1987 really goes into this in detail and discusses each one of these things in detail. Okay, so the point is gyrosynchrotron theory is pretty complicated. We need numerical models to actually interpret the spectrum and fit the spectrum, as I'll show. There are simplified versions of the theory that are just analytical expressions. For example, Dulk 1985, say if you have mildly relativistic electrons, there actually is simple relationships between that peak frequency there and the magnetic field. You can use that as a diagnostic of the magnetic field, and people do. It's very useful. The slope on this side here is called the spectral index. That's actually related to the spectral index of the electrons, or how non-thermal they are, and that's also a really useful diagnostic. So if you don't want to go down the route of numerical models, this paper here kind of describes a more simplified theory. Yeah, so how is it used in literature? So it's actually used quite a lot in the microwave regime. So this is just a nice paper of a flaring active region, and at various points in the active region between, what do we have, 2 and 20 gigahertz from Owens Valley. The blue points show the shape of the spectrum here, and you can see each point has a pretty characteristic gyrosynchrotron shape, and the red line is the fit of a model from which they're able to get different values to the magnetic field and the electron spectral index, as I showed here. So as you can see, the magnetic field in this flaring active region varies between 140 and 520 Gauss. And in fact, radio is probably, someone maybe correct me, is the only way you can actually measure magnetic field in an active region, is particularly in flaring as it develops over time. And since the magnetic field is what drives the flare, this is a really powerful diagnostic to be able to get at. I've done this for a CME as well. Diana showed the really famous case of the Bastian et al. Paper where they imaged the radio CME. The radio data flux versus frequency again had these points here, to which we fitted a gyrosynchrotron spectrum to get at all of these parameters of the CME, so magnetic field, density, all sorts of things. And you can see the magnetic field of a CME is often a lot smaller than the original flare. It's down in a few Gauss, and this is typical, but being able to measure this in the CME is pretty rare. In fact, this paper here is probably 1 of 10 times that CME magnetic field was actually measured. So, you know, with more sensitive measurements in the future, hopefully we can actually get at gyrosynchrotron emission from a CME. Okay, how are we doing for time? I'm a little bit behind, I guess. So we move on to the last emission mechanism, which is plasma emission. This is probably the most complicated and most still under active research in terms of the plasma physics involved. So let me see. Yeah. So yeah, when we get a flare, as Diana showed, you know, you can have open magnetic field and you can have particle stream on that open field. And these will emit something called plasma emission. The energy range that the electrons are in when they do this is maybe around, let's say 10, 30 keV, maybe as high as 100 keV, and they emit plasma emission. So the plasma that or frequency that you observe is dependent on the electron density, as I showed, and as the electron density drops, the plasma emission from a type 3 beam, as we've seen in frequency versus time, looks a bit like this. You get lower frequencies over time. The brightness temperature of plasma emission tends to be really high. You know, in say 100 megahertz, it could be 10 to the 9, 10 Kelvin. as it gets lower in frequencies, it can be as high as 10 to the 15 Kelvin, which is clearly not an actual measure of the plasma temperature. Okay, that would be kind of unphysical. This means it's a coherent emission mechanism from plasma oscillations. So yeah, the emission is impulsive and coherent, and it can be associated with X-rays as well. So it tells us, you know, it's associated with energetic electrons. So what actually causes this emission mechanisms? How do we go from an electron beam to radio waves? It's a multi-stage process. It's pretty involved. As I said, each one of the stages is kind of an active area of research, but the original mechanism was proposed by Ginsburg and Zeleznyakov in 1958. And we start with an electron beam. This electron beam produces what's known as a bump on tail or a two-stream instability that I'll show in the next slide. And this produces a plasma oscillation. As we showed at the start, it means the background plasma oscillate, or electrons oscillate collectively, like in the illustration at the start. And then after here, it gets pretty complicated. So how do you go from a plasma oscillation to radio waves? Well, there's a couple of routes, okay? So the plasma oscillation can result in radio waves at the fundamental plasma frequency and the second harmonic plasma frequency. And they usually get there by interacting with other wave modes of the plasma. In fact, this route will be, there's ion sound waves, off of which the Langmuir waves or the plasma oscillation scatters to produce this. And I'll go into how that happens. And there's also scattering off of ion sound waves. It creates more plasma oscillations that coalesce with the original. In fact, we had a question about that yesterday, and produce second harmonic emission, okay? So I'll try to go through this step by step and describe, kind of give a general overview how each of it happens and references to some papers that discuss it in more detail. Okay, so the first thing that we have when we have electron acceleration in the corona is the development of what we call a bump on tail in the electron distribution. So electron distribution versus speed here, we have the Maxwellian. And because we've accelerated electrons in the high energy tail, we have a little smaller Maxwellian, what we call a bump on tail, okay? This bump on tail is actually unstable to the growth of Langmuir waves, and it leads to the bump on tail instability. How we actually measure or observe this, or theoretically treat it, is we look at the distribution of Langmuir waves or plasma oscillations. They're the same thing, or almost the same thing. So this is Langmuir wave energy with respect to speed, and we get growth of Langmuir waves in this region of velocity space here. In fact, you get a growth of Langmuir waves when the phase speed of the waves match the speed of the beam, okay? This is what causes the instability. How that actually happens is actually pretty in depth. There's a great description of it in this book here, if you're looking to go into the real detail of the theory involved in how this instability grows. But in general, you know, its growth and its evolution over time, how the beam propagates, how the waves grow in their phase space, is treated in something that we call quasi-linear theory of wave-particle interaction. And basically what we do is we look at the development over time of the electron distribution and the Langmuir wave energy distribution. And you can see that they're coupled here, that the electron distribution depends on the energy in the waves, and the waves, how they develop over time, depend on the electrons. So these two things are coupled together, and we numerically solve these things and allow it to develop over time just to see how waves grow and how the beam dissipates in space over time. So you may have noticed here that this takes on what we call an advection diffusion equation, okay? So this is kind of a pretty standard equation in physics. It basically describes if we have a distribution, how does it move in space? You know, it will probably move forward in space, obviously. And D describes how it diffuses or spreads out in space, okay? Now, one of the key points here is that the diffusion of electrons in this bump-on tail depends on the energy in the Langmuir waves. So in fact, the presence of these will cause the electrons to sort of not lose their energy, but spread their energy in space, okay? The growth of the Langmuir waves depends on this dFdV here. So this is key to all the instabilities. You have a positive gradient in the electron distribution function. Sorry, this is what causes the growth of the Langmuir waves in their space, okay? So it's pretty complicated, but what we do is basically model these two distributions over time using these differential equations, and they get a little bit bigger and have more physics involved. In fact, I'm running out of time, so I'll keep going here. Usually what we do is we take, distance into an atmosphere, electron beam speed, and we allow this to develop over time. And I'll show this movie here. You can see you'll see the electrons propagate a long distance. And then we model the growth of the Langmuir waves in their phase speed space over time. And basically what happens is they propagate together in space, and they form what we call a beam plasma structure. So as the electrons propagate, they excite Langmuir waves all along the way. And those Langmuir waves, they kind of follow the electrons, and those Langmuir waves eventually are the things that end up producing the electromagnetic emission.
Oh, and okay. Where's this movie from?
This is one I did myself recently, but I should have, yes. Okay, so I have no time to describe all of this, but you'll see this in Reid and Contar. In fact, Hamish Reid that's his code that he runs this off of. And a really nice overview and breakdown of all of this complicated theory is in Reid and Radcliffe 2014, in which they give a review of type 3 radio bursts.
Cool.
Okay, so this, I've showed these coupling equations here. So electrons and Langmuir waves, how they develop over time. This is a simplified breakdown, and this is all of the different physics that goes into this process. I've no time to go into it here, but as you can see, it gets pretty complicated. But if you're interested in the detail, yeah, I give Reid and Contar a read, and Reid and Radcliffe a read. Okay, so for the last slide here, I know I'm pushing time here. We talked about it's a multi-stage process. Once we have those plasma oscillations, how do we get to the electromagnetic emission? This, again, is a really in-depth and complicated field, but we usually measure it by something called wave-wave interaction. In other words, the combination of a Langmuir wave plus a sound wave gives us an electromagnetic wave. The criteria upon which this happens is that we have to have frequency matching here. So the frequency of the electromagnetic wave has to equal the frequency of the Langmuir wave plus the sound wave. This is basically an energy conservation criteria. Same for the wave numbers, that's a momentum conservation criteria, okay? I won't go into it in any detail. In fact, I probably had to do on the next slide, but I'll skip over it because I'm out of time. If you're interested again in this theory, these are some great papers to go back to. In fact, this entire process is so, I guess, state of the art in terms of plasma physics. It was only given a full numerical treatment from electrons to electromagnetic waves in 2008, 2009 from this Lee et al. Study here. So it's as you can tell, it's really modern and in-depth plasma physics, and there are still some questions along the way about how it all works. I will skip that because I'm out of time. Yeah, so we've seen some examples of this process of electrons streaming into the atmosphere, as Diana showed. As they stream into the atmosphere, they produce this bright, intense emission, over time and frequency. And here's another great example from Reid et al. Again. An electron on a closed magnetic field producing plasma emission. The brightness temperatures here are very intense. So yeah, I've had to speed through the end of that there. So I'm just at the end now. The things I've covered a lot in an hour. So there's been a huge amount, and I've also left here things I haven't covered, like elements of radiative transfer, other types of synchrotron and gyrosynchrotron emission, And I would need a whole other hour and maybe more to cover that. So I'll leave it there. Thanks.
Awesome, great, Eoin. Do you have any
Yeah,
questions?
that was fantastic. Thank you.
I assume there has to be some questions on that. There was an awful lot of stuff. No one can
Yeah,
understand
sorry,
really.
I probably could have done it with half the stuff.
I know, it's great.
Hopefully we can share the presentations online. I don't know if
Sure,
that's...
yeah, definitely.
Okay.
I was just going to say thanks a million, Eoin. Like, for someone who may or may not be writing up a thesis, it seems like a valuable resource. This whole presentation here.
You can copy it all, Pierce.
Yeah.
No questions.
There's one thing, sorry, I'm cutting across somebody there. I was interrupted at one point while you were talking about the gyroresonance and the differences between gyroresonance, gyrosynchrotron, and then the one after it. I was wondering if, I think it was when you were showing the arrows, what changes with, what am I trying to say? So all of this, I came in when you came back to this slide. So this is just gyrosynchrotron, is that this is nothing to do with super relativistic electrons or anything, no?
This is just gyrosynchrotron. Well, it's important to note there are relativistic electrons, in there that we often in the simulations feed in MeV, maybe 10 MeV energies, and that's starting to get to relativistic effects as well. But the synchrotron is highly relativistic, even up to hundreds of MeV. You know what I mean? Which we don't usually come across in solar flares, or maybe we do. Correct me if I'm wrong, Laura. You maybe know those electron energies well.
Yeah, it's hard to tell, I guess. Actually, just building on that own, from that plot, what would gyroresonance source look like?
It looks like the spectrum.
Yeah.
My guess is because it's thermal, it would end up having the frequency squared spectrum of the Rayleigh-Jeans law. I think I might be wrong on this. No matter what the emission mechanism is, if it's thermal and optically thick, what ends up coming out of the plasma is basically a Rayleigh-Jeans.
Okay.
So it would be pretty simple to diagnose. If you see that frequency squared, people usually say that's thermal. I need to double check that though, but I maybe put it in the Slack.
Cool, thanks. That was great, by the way. Thank you so much. Fantastic.
Okay.
So, Eoin, what do you think is our best hope for getting better resolution observations in terms of quantifying and characterizing the features that we see in the radio? Just try to observe in a little bit higher frequencies, or?
Yeah, well, in the low frequencies, we're destined to have these boring images of the sun. But it's really debated. I mean, people say if we have long baselines, do we observe more compact sources? There's a little bit of evidence to do with that. I know Pietro, you were working on that a little bit. Also, Eoin was working on using a deoccultation of the moon during solar eclipse. And that can get you at higher frequency or higher spatial resolution than you normally would. That reveals some tentative evidence that there is small scale structure in the low frequency sun. So I think we should still study it and see how small that structure is. But it's probably not as bad as we see here. There is some bits and pieces. I don't know, Pietro, if you've anything to add to that.
I think, maybe before Pietro speaks, I think we can try to move with higher sensitivity and more signal to look a little bit further out from the sun, and there those effects of scattering would be fewer, I guess, and weaker. Also, the raison suppression would be lower, so we could try to see something, but you'd need more. I guess you would need more sensitivity. Yeah.
It's for sure worth studying because people are starting to get back into it now. I think Mohammed has a question.
Yes, it's just a quick question. I was wondering what is the highest frequency in the radio band that we can theoretically observe, or what's the lowest height in the solar atmosphere that we can probe using a radio emission?
It's a really good question. If at the end of this movie you saw you can still see the movie, I hope, 17 gigahertz gets you to the chromosphere. Nowadays, with the advent of telescopes like the Atacama Large Millimeter Array in Chile, you can get into the terahertz regime, and that starts to get you as well into the chromosphere. Any more than that, if you move into the infrared, you probably go below that, but then you're outside the radio. So I would say the radio, the cutoff is the chromosphere, and beyond that, we can't go any further. And that's terahertz, like very, very new interferometers can do that now.
Right. But also keep in mind that we have to be around the sweet spot of magnetic strengths in the corona, because that's where the interesting stuff is happening, right?
Yeah.
You can see how you go into more thermal emission as you go higher up.
Yeah, for sure.
Yeah. Thank you.
Okay, maybe.
Eoin?
Yeah.
Concerning about previous discussion about the resolution, you mentioned if the eclipse interferometry work that was very beautiful, but as you know, the scattering happens mostly in the solar atmosphere near the local plasma frequency area. So when it approaches the Earth and the Moon, the scattering is not strong. So theoretically, you can see the cutting edge, and practically, if I did that, so yeah, but that doesn't mean there is. We can see such fine structures in imaging near the sun. So if we want to see very compact sources near the sun, the only way is to observe the high order harmonic waves, I think.
Yeah, indeed. Actually, that's a little bit what I wanted to add, and I will tell more in my talk later. But of course, the scatter is really important, and we will have for sure, as Eoin said, always look at these boring pictures at larger frequencies. But there is some hope, because by using remote stations in LOFAR, we started seeing hints of like some finer imaging that we, for example, didn't see with using only, less than 2 kilometers baselines of Nancy. But again, if you look at the fundamental emission, then no, you're not going to see. You see large blobs. You see actually large blobs moving erratically all over the place. But as Beijing said, if you look at the harmonic, because we're away from the plasma frequency, or where the local plasma where the waves are generated, and then I think there is some hope for that. So maybe later in my talk I will show some hints of that.
On that note, I don't want to stop the discussion, but we should probably have a little break before we run into this next talk.
Yes, sure, for sure.
So what do we? We'd scheduled for the next talk to start in 5 minutes. Maybe if we give people 10 minutes, does that sound about
10 minutes? Yeah.
Reasonable, yeah. So we'll come back in 10 minutes. Yeah.
Okay.
Cool. See you around 10.
Thanks so much, Eoin.
Go on.
Sure.